Hi everyone. Today when I hold my office hour, one student told me she wants to see a few more examples, and then I'm making this video to show you one more example on the analysis of the algorithm. So I'm gonna start from a coding challenge. You are gonna be able to do that, and then after we finish the coding part, and then we are gonna do a algorithm analysis. We are gonna figure out the big O, big omega, and eventually the big zeta. Okay, so let's see this question. This question is create a program that takes a list of n values as integers and return a new list of values with every values in the original list doubled. Okay, so let's see, this is the input, and now let's start to build that algorithm. So the first thing is I want to do a new list doubled equals a empty list. And after that, I want to do an iteration, say for I in my list, and then colon. And I'm going to do the value doubled. So the doubled, nope. uh, doubled value equals I multiplied by 2. Okay, so the value is doubled, and then I'm going to do append. So new list doubled dot append, and then parentheses. I'm gonna put the doubled value here. Okay, so I think that's it for my algorithm. Just to do a double check, let me check the new list doubled and see if I have all the right values. So I have 2, 4, 6, 10, and 12. Okay, yes, they are the right values. So my algorithm is done, and then I'm gonna take out this print. Okay, so, and then this part, highlighted part is my algorithm, and I want to analyze this algorithm. And instead of having a list given, now I'm gonna say, how about I don't have this list? And then I have just a list of n values. And how many values? We don't know, but there is an input size. And then we assume that the input size will be n. So I'm going to write a comment say, and input size equals n. Okay, and then giving the knowledge that the input size is n, now I want to visit my algorithm. I want to visit each line of the code and analyze that to figure out with a input as n, how many times I'm gonna run each line of the algorithm. Okay, so how about this part? The first one. This is not part of any iteration. We build a empty list and then we only run that once. So I'm going to do a 1. Or I should do 1 multiplied by C1. So we are assuming that the cost of this line is C1. And C1 will be a constant time. And how about this part? For I in my list, this line of the code, how many times are we running that? If there are n values in the list, and then we are going to run this for n times, right? So n multiplied by C2. And how about this one? For this line of code, are we also going to run for n times? Correct. We are going to run for n times. So how about I just do a copy and paste C3? Okay, how about the next one? The next one is also going to be run for n times, and let's do a C4. Okay, so let's put them together. If I put all the costs to execute this algorithm together, and I'm going to do a comment, what is Tn? Tn is C1 and plus C2 plus C3 and plus C4 and multiply by n, correct? And then you will say, that's annoying. Well, why do we have the C1, C2, C3, C4 and plus? We don't know what are their values. And this brings us the idea of the primitive step. Remember, for the primitive step, it could be a definition It could be one line of the iteration. It could be one line of the body of the iteration where we do some arithmetic manipulation and then we assign that to a new value or we append. So for those things, they are primitive steps because we know it can be done without triggering any hidden harder manipulation that we don't know. Well, let me give you an example. Say if you have a list, if you do sum my list, okay? So for this line, it seems that it's also one line of code, but is that really a primitive step? The answer is no. Why? Because for that line of code, well, there is a function behind the thing. And to trigger that function behind the scene, and then what will happen is that function will visit all the values one by one and then add them together. So even if this is one line of the code and it is just a function behind the scene and that function is linear. And I find I don't like this solution because this will trigger a append. For that append, that is a method call, so it's not quite clear if it is primitive or not. So let me change my solution a little bit. Instead of doing this part, I want to do equals my new list doubled and plus parentheses square brackets doubled values. Now I'm doing a concatenation of the list. Okay, well, and then this is easier to read because I'm not triggering any function or method behind the scene, and this is clear that this can be counted as a primitive step. Okay, and after that we know this is a Tn, and now we are gonna assume all the primitive steps take the same time, which is 1. Okay, and then if we assume that C1, C2, C3, and C4, they are all 1s, and then what is the Tn again? This will be 3n plus 1, right? Okay, so that's good. We have a polynomial, and starting from a Tn as a polynomial, what's the next step? For the next step, we want to figure out the big O and the big omega, so upper bound and the lower bound. Okay, let's see how can we do that. So let me do the big O. So for the big O, we want to increase that a little bit to find a polynomial which is always higher than Tn, right? So how can we do that? Let me see. So if we want to do a, let's try, Tn is always going to be smaller or equal to 3n plus 1n. Is that always true? Is that always true? Not always. When n value is greater than 1, how about that? So if n value is 0.5, and then you will find Tn is actually greater than this one. But if n is greater than 1, and then this version will be greater than this version, guaranteed. Okay, so I'm going to put in a constraint, say n value is greater than 1. Or if you want to be safe, you want to say n value greater than 10, that's also, you are also right. So you don't have to be that accurate. Well, the goal of the algorithm analysis is we are worrying about the input get really large. We are not worrying about the really small inputs. So if I want to put 10 here, that's also fine. Okay, and then this part will be smaller or equal to 4n, right? Okay, so, and then we see Tn is always smaller or equal to 4n if n value is greater than 10. So we have found an upper bound. So Tn is smaller or equal to C multiplied by Gn when n is greater than n0. And now let me explain in which c equals 4, right? So c equals 4, and that's a constant, and n0 equals 10. Okay, we are using 10. If you want to use 1 or 2, that's also okay. And gn is n. So gn is a polynomial of n. So after we have found the upper bound of the tn, what does this mean? This means this tn is big O n. Okay, so this is the first part. We are doing the big O. And then I want to do the big omega. So for the big omega, we start from the Tn again, but we want to have the lower bound instead of the upper bound. Oh no. Okay, so for the Tn, now instead of finding a polynomial which is higher than Tn, now we want to find a polynomial which is slightly lower than Tn. So how can it be? So, oh, I see an easy solution. Because Tn is 3n plus 1, right? Tn is always going to be smaller or equal. It's always going to be greater or equal to 3n. How do you like that? Okay, 3n plus 1. And then if we drop that 1, we are just decreasing the value by 1. So Tn 3n plus 1 is always going to be greater than 3n. Okay, that's easy, right? And then, well, let's do this way. So we have found an lower bound, colon, and Tn is always smaller or equal to c multiplied by gn when n is greater than n0. And by the way, for this part, Tn is greater than 3n, and is true for all the values, all the n values greater than 0. Okay, well, and then I can say again, in which c is 3 and gn is n and 0 is 0. Okay, so after putting this information together, we can say Tn is I don't know how to type omega, so I'm going to spell that out. Omega n. Okay, so we have just proved that for that given algorithm, we started from the algorithm here, and then we got the Tn figured out, and from the Tn, we have proved that the big O is big O n, big omega is big omega n. So what is the big theta? Big theta is theta n. Why? Because if we have proved that it is O n and then also omega n, and putting them together, that is a big theta n. Okay, so this is a another example that we started from coding a small algorithm, and then we move on to do the algorithm analysis. Okay, and this is what you are expected to know how to do from this course. And this is just a one additional example. And thank you for suggesting that. Should I say your name? Probably no. Okay, so well, for the student who suggested it, and thank you for suggesting so. And if you want to talk to me, well, remember my office hours are online on Mondays and Thursdays from 1 to 2. Okay, so that's it for this video, and I will continue later.